In this video, I want to take a look at a couple of different ways how we create subspaces from other things, right? So here's the first of the ways. Theorem. If I've got W1, W2, W3, all the way up to Wn that are all subspaces of a vector space V, so I got a bunch of different subspaces of vector space V, then I'm going to create a new set here, W, which is the intersection of all those other ones. This upside down thing means intersection, right? That means the stuff that's in, if I just had W1 intersect W2, that would just be the stuff that's in both. If something's in one but not the other, that's not part of the intersection. It has to be in W1 and W2. So the intersection of all n of these things would be the stuff that's in every single one of them. Okay? If it's not in one of them, then it's not in the intersection. Okay? So my claim is that this intersection is also a subspace. So from a bunch of subspaces, I can create another one by just taking the intersection where they all overlap. Here's my proof. Now, we've already seen in previous video that to show that something is a subspace, we really only need, since it's already a subset, certainly everything in W is in V, because everything is in W is in all of the Wn's here. So I have a subset of V, I just need to show that it's a subspace. So I need to say, is it closed under vector addition and scalar multiplication using the same operations as V? So let's see. Take two vectors in W and add them up. See if see if axiom 1 works. Now, because W is the intersection of all of these W1, W2 up to Wn, we know that V1 and V2 are in each one of those W's. W1, W2, we're going to just say Wi for each I on the end. We're given that each one of those Wi's is a subspace. So if it's a subspace, it's closed under addition. So V1 plus V2 then also has to be in each one of the Wi's, because each one of the Wi's is a subspace and the V's are in those things. So V1 plus V2 is in each one of the Wi's, and hence we can conclude that V1 plus V2 is in W, because W is the stuff that it's the intersection of all of them. If you've got something that's in each one, then that's what the intersection is. So V1 plus V2 is in each one of the W1, 2, 3 up to Wn, and therefore it's in W. So we are closed under vector addition. In a similar way, you could say, let K be any real number and look at KV1. Well, again, because V1 is in W, because V1 is in each of the Wi's, KV1 also has to be in each one of the Wi's, because the Wi's are subspaces and hence closed under scalar multiplication. Then KV1 must be in W because it's in each one of those things, and hence it's in the intersection of all of those things. So it's closed under scalar multiplication, and we have proof that it's a subspace. Here's an example. Right? In R3, take a look at W1 is going to just be the plane x plus y plus z equals 0. It's just a plane that goes through the origin, and it has a normal vector 1, 1, 1. And W2 will be this other plane, x minus 2y plus 3z. It is also a plane through the origin, but now the normal vector is 1, minus 2, 3. So these are two different planes, both going through the origin. What does the intersection of two planes look like? Well, two planes might actually not intersect. They might be parallel to each other. But we know that these do intersect because they both go through the origin, right? If you plug in 0, 0, 0 for x, y, and z, either in this equation here or that equation there, you get a true statement. So we know they do intersect. So two planes that intersect have to either be the same plane or they have to intersect in a line. Well, it's going to be a line through the origin because the origin we know is on both planes. So the origin is part of the intersection. And so the intersection of those two planes through the origin is a line through the origin, which is another subspace of R3. Right? Now, you can you can come up with this parameterization in several ways. You could use your systems of equations knowledge and say, I got a system of this equation and that equation, and find the solution set, parameterize it, and you can see that it would describe this line. What I did to get this parameterization is to say, I know the two normal vectors, so the cross product of those two normal vectors will be perpendicular to each of those vectors, each of the normal vectors, and hence it will be parallel to both of the planes. And since I know 0, 0, 0 is the point that this line goes through, I can describe this line that way. Now, so that's the first way we have of creating another subspace from known subspaces. And the next way I want to look at is going to take a couple of definitions here. And this first definition we may have seen earlier in the course, but I want to reiterate it here because it is an important one to know. I'm going to use this a lot over the rest of the course, actually these two definitions. So given a set of vectors, v1, v2, all the way up to vn, in a vector space V, we define a linear combination of these to be k1 v1 plus k2 v2 plus all the way up to kn vn, where all those k's are real numbers, right? A linear combination I think of as a sum of multiples. Each one of the v's gets multiplied by a constant, and then they all get added together. So it is a sum of multiples of the v's, right? Now, I think we saw this in using matrices and trying to describe matrix multiplication and things. I know the book talked about linear combinations of things at that point, but it means the same thing. If you've got a collection of things and you multiply each of those things by a number and add the results together, that's a linear combination of those things. That's what linear combination is. Now, more specific in a vector space here, I want to talk about a span, or the spanning set. So given a set of vectors S, v1, v2, up to vn, notice this is a finite set. It's not just infinitely many vectors. It's just, 2, 3, 17, whatever it is, but it's a finite set of vectors. I define the span of these vectors, or the spanning set of these vectors, to be the set right here. The notation is span S, and it is the set of all linear combinations of v1, v2, up to vn. So all the stuff that looks like that for every single possible combination of k1, k2, up to kn that you can think of. Or even if there's some you can't think of, just if it's possible, take that linear combination, stick it in here. All the linear combinations of those v's. That's the span. Okay. From the point of view of, if this set S has only one vector in it, when you look at the span of that one vector, that this sum just looks like multiples of that vector. So you got that vector pointing in a particular direction, and you keep stretching it out by different amounts, or maybe multiplying by negative, so it's going off in the other direction, and you just be describing a line. Right? If you're taking the span of two vectors, then maybe you're describing a plane. Not maybe, you are. The span. The theorem that I have here is that the span of a set of vectors is a subspace of the vector space V. Right? So this is all under the same conditions in the definition here. So if I have a set of vectors v1 to v2, I'm calling that set S. Maybe it's right here. Right? Set of vectors v1 to vn, call that S. Then the span of S is a subspace of the vector space V, and V is where those vectors came from. Right? All those vectors are in V. The proof that it's a subspace, well, how do I prove something's a subspace? Well, I could either show all 10 axioms of a vector space are true, or because it's a subspace, not just we're not acting blindly. We know we're already in a vector space, so I know a lot of the axioms already hold. All I need to do is show axiom 1 and axiom 6. So here we go. How do I show axiom 1? Well, pick two vectors in your set and see if when you add them together, you get another vector in your set. They have to be arbitrary vectors. You can't take two specific ones and add them. So let W1 and W2 be in the span of S, so the set of all linear combinations. That means W1 has to be written some way here, K1 V1 plus K2 V2 up to Kn Vn for some values of K1 up to Kn. And likewise, W2 would be some other linear combination C1 V1 plus C2 V2 up to Cn Vn. So my two vectors I'm choosing, I know they're in the span, so I know they are linear combinations of V1 up to Vn, and I'm just writing down what those linear combinations are. Now, if I add those two vectors together, W1 plus W2, well, here's W1, here's W2, and I'm going to do some rearranging here because we're in a vector space, and I know that addition is commutative, and there's distributive properties and whatnot. So the first thing is I'm going to rewrite, I'm going to take the K1 V1 from here, and the C1 V1 from over there, and then the 2's, and then the 3's all the way up to the n's. And I notice that these first two terms have a constant, and that's not a constant, well, it's a vector, V1, that can be factored out. So K1 plus C1 times V1. Likewise here, there's a V2 that can be factored out, and so on. And look at what I end up with. I end up with some constant times V1 plus some other constant times V2 plus all the way up to some nth constant times Vn. I have a linear combination of V1 up to Vn, which means this must be in the span of those vectors because the span is all of the linear combinations. So if it's got all of them, it must have this one. And so V1 plus V2 is in the span and addition is closed. Right? Likewise, to see that scalar multiplication is closed, right? If I have a vector, same W1 here, so this is a vector that's in the span of S, so it's some linear combination of V1 up to Vn, and I multiply it by the constant t, well, that would look like this, and then I can use distributive property and multiply the t's in there. Well, when I multiply the t's in there, what I get is tk1 times v1 plus tk2 times v2 plus all the way up to tkn times vn. I've got a linear combination of v1 up to vn, which means I have something that's in the span of v1 up to vn because it's a linear combination of those things, and the span is all of the linear combinations, including this one. And so kw1 must be in the span of S, and S is closed under scalar multiplication, and therefore S is a, not S is a subspace, the span of S is a subspace, right? S is the small set of vectors. It's only got finitely many things in it. The span of S has infinitely many things in it, right? Because the k's are real numbers. They can be anything from minus infinity to plus infinity, and you're taking all the possible combinations that you can, and so you've got infinitely many things. The subspace has infinitely many things. The space you started with, S, not the space, the set you started with, has only finitely many things. Here's an example. I'm in the subspace P2, so this is polynomials of degree 2 or less. Right? And I'm going to look at, oh, well, I'm just claiming that the span of 1x and x squared is actually all of P2, right? Take any polynomial you want, like any second degree polynomial, right? So 3 plus 2x plus 5x squared. So it would be 3 times 1 plus 2 times x plus 5 times x squared. You've got a linear combination of 1x and x squared as described here. So all polynomials of degree 2 are written as linear combinations of 1x and x squared, and everything that's a linear combination of 1x and x squared is a second degree polynomial, or less. It could be less because you could be multiplying x squared times 0, in which case it only looks like a first degree polynomial, but that's fine. It's still second degree or less, which is what P2 is. Okay? Planes through the origin. Think about how we described planes parametrically a couple of sections ago, right? If we had two vectors, say 1, 2, 3, and 2, minus 1, 4, if I look at the span of those things, I'm looking at everything that looks like x, y, z equals k1 times this first one plus k2 times the second one. This is a plane that is actually a plane through the origin that's parallel to both of those two vectors. If we wanted to not go through the origin, we'd have plus some other constant vector here. But through the origin, it's just a linear combination of two given vectors. Okay? So the span of those two given vectors is the whole plane, is the whole subspace, which is the plane. And lastly, I think this is lastly, yeah. We don't necessarily think of this as vectors, but they behave like vectors. The vector space of functions, right? Take two functions, sine and cosine. What is the span of those two functions? Well, it's all the linear combinations. K1 sine x plus K2 cosine x. You know, 3 sine x minus 2 cosine x is one linear combination of sine and cosine. There's times when, when I think about the vector space of functions, it's like it's so big. There's so many functions. It's like it's not even nearly as well organized as R2 or R3 or Rn for anything. It's so much bigger, and we'll discuss that when we talk about dimension in a couple of days. But pieces of it I can clearly see. That is, the notion of taking a linear combination of these two functions is very similar to the notion of taking a linear combination of these two vectors. And so if I look at all the linear combination of these two vectors, I can see a plane. So when I look at all the linear combinations of sine and cosine, what I visualize is a plane out there in whatever this vector space of functions looks like. I don't really know what it looks like, but I know what that plane looks like. It's this flat thing that just kind of cuts through it. One direction is the direction for sine, another direction is the direction for cosine, and I'm just filling in all the linear combinations in between, and I'm making that plane. Okay? So visualization for me in all of this comes down to how does whatever vector space I'm in, how does the corresponding thing look like in R2 or R3? And that gives me somewhat of a visualization of what might be happening over in that other vector space. Anyway, there's a couple of different ways to thinking about subspaces and generating subspaces from other things.